Thank you, Sato-san. Welcome, everyone, and thank you for joining this presentation. Minasan yokoso, kono presentation ni go sanka itadaki, arigatou gozaimasu. I tried that phrase about 30 times, so I hope it came out all right. Such a difficult language. Anyway, I'm very happy to be here and take you to a short trip talk through global research with a focus on the role of Netherlight and SURF in international collaboration. It's my first APAN, and many of you don't know me, so I will shortly present myself. My name is Karen Wessel. I'm a product manager for Netherlight at SURF, the Dutch NREN, and at Netherlight, the global exchange point in Amsterdam. I help researchers, universities, and institutions to connect at the speed of light, if they want to. Fun fact, when I'm not working on high-speed networks, I also play traditional African instruments like the adungo and the dingidi. Oh, sorry, I'm forgetting to click here. They are African instruments, and I like to do this when I'm not working on networking. For those unfamiliar, SURF is the Dutch NREN. It's a cooperation, a member-based association for ICT infrastructure, and we provide ultra-fast, innovative digital infrastructure for universities, university hospitals, research institutes, and also universities of applied sciences. So if you're a scientist in the Netherlands working on AI, medical research, high-energy physics, astronomy, or any other field, chances are you are using SURF's network and services. At first glance, Japan and the Netherlands may seem very different. Japan is large and mountainous, and the Netherlands are flat and small. But both nations are leaders in digital innovation and highly advanced in their networks and technology and research. Beyond the internet, we are linked by our NREN, SURF on the Dutch side, with the National Institute of Informatics in Japan and their SINET, and also working a lot with KDDI and NTT on various operations. So we are all regularly in touch to collaborate. Together with all the other NRENs in the world, we enable some of the fastest research networks in the world, facilitating groundbreaking research and science. Our fiber optic cables aren't just cables, they are highways for innovation and collaboration and science. And we're not just sharing fiber optic cables, we're also sharing some cultural icons. Biffy, or Nijntje, as we call her in the Netherlands, is Dutch, but usually popular in Japan. And I wonder who of you in the public can see who I'm holding in my hand. For the observant viewers, I'm holding Bitcoon, NII's mascot. It's a PR apprentice working on promoting informatics and science, and she has, or he, distinctive eyebrows and a very nice jumpsuit coat. Well, that was the fun part. Now we'll get to the serious part. The Netherlands and Japan have a very long history of sharing knowledge and working together on very many science projects. I could probably fill 10 or more slides with special use cases. But, and here you can see a few that you can find information about on the university websites and elsewhere. And further on, I will highlight just two of them a little bit with more detail. But first, let me focus on the role of Netherlight. Netherlight is the Dutch open exchange located in Amsterdam and run by SURF. And it connects institutions worldwide via high-speed dedicated light paths. It's designed for data-intensive research and global collaboration. For redundancy, we operate from two separate locations in Amsterdam. The bigger node is a Juniper MX 10008, and the smaller one is a Juniper MX 480. And Netherlight currently offers interconnections via Ethernet VPN, multi-point or point-to-point, up to 400 gigabits per interface. Here's a look at the various connections to Netherlight on the southwest part, you see some cloud providers that are connected to it, and that some of the universities, members, institutions of SURF are using services from. And then you see most global NREN partners connected to it at the rest of around the bowl. And you can see Japan, NTT, NII, SINET, KDDI. I thought I'd just mention them all because we work together so much. And they were recently upgraded to 400 gigabits redundant. In today's research landscape, secure high-speed connectivity is no longer a luxury, it's a necessity. Fields like high-energy physics, astrophysics, but also genomics, very many various domains of science, they generate massive data sets and it's only growing, and we need to be able to move them across the world fastly and securely. And this is where global exchange points play a critical role. And as a community, we have established very many years ago that we would use these EXPs to transfer these data for research data exchange around the world, and then from there to the NRENs that are connected to it. Here's a Géant map of EXPs. Thank you, Géant, for providing this. I don't know if there's anyone from Géant in the public, but you can find this on the Géant website, and then you can click on one and it'll highlight who's connected to it on both sides. And I have clicked on the Tokyo-Amsterdam connection here. Of course, this doesn't represent the path that it actually does, but it's a visualization. And like I said, that one was recently upgraded to 400 gigabits, connecting Japan's NII with Netherlight. And Netherlight is also not just a connection, it's part of a very big, larger global network community that you are all part of, that very many NRENs are part of in all countries. And SURF and Netherlight are actively involved in international collaboration in these consortia and associations around that. So for instance, AER, GNAG, ANA, Géant, just to mention a few and others. And I realize that I'm comparing apples and oranges here, but I just wanted to mention some of them as frameworks within which we collaborate with others. And we attend regular meetings, and we are actively involved in the community engagement and involvement from within those collaborations. And this, at SURF, we think that this global participation, we are quite internationally oriented, helps us to obtain continuous improvement for our scientists and researchers. On the transatlantic side, many of you will have maybe seen this. We also bring in connectivity into the ANA system. That is, of course, a system with very many partners. I think it's 9 NRENs now part of it. And together with Nordunet and Canary, we are upgrading the current link from Netherlight to Moxie link in Montreal in Canada to 400 gigs in September. That will be affected. And as James Deaton from Internet 2 pointed out yesterday, I don't see him here, but I see Thomas there. There are various upgrades going on in the ANA system, also from the US to Europe. So this is just one of the many links that are part of the system. Both from a network engineering and a geopolitical point of view, we think it's important to have enough redundancy and resiliency to keep our researchers doing what they need to do. And with Géant and Nordunet, also within Europe, we actually have some spectrum sharing agreements in place. We swap or share spectrum on some connectivity within Europe as well. Of course, global collaboration isn't just about cables and connectivity, it's also about the projects and the use cases, and I'd like to highlight two of them. The first one is an experimental network demonstration that took place at Supercomputing last year, November, in Atlanta. And it's a multipath data experiment led by Japan's NICT, NII, and Géant. and using MMCFTP, which stands for Massively Multi-Connections File Transfer Protocol, they moved data between Japan and the US over 10 different 100 gigabits connections simultaneously, and 3 of these were led through Netherlight. This wasn't just a technical trial, but in my view, equally important, a showcase of what we can do as a community when we collaborate together and we trust each other and we can call each other up, mail each other, Slack each other, and get things done. And also, it doesn't matter if some of the things maybe fail or it doesn't go as well as we wanted to, because we learn from it, and I think that is the important take from these experiments. In this experiment, there were, I think, more than 20 participants, so I'm not going to mention them all, but there are various websites, and there's a press release where everybody is mentioned. And so Netherlight was just one of those 20 plus. Well, I think, yeah, very many NRENs and GXPs were involved. This slide definitely has too much text, but maybe you want to read it later, if we can find a way to share these slides. It was a use case that I wanted to highlight. It's an agri-tech collaboration where Japan and the Netherlands work together on solving food challenges together. Japan's aging population has led to labor shortages in agriculture. And by combining Japan's robotic expertise with Dutch greenhouse knowledge, technology, scientists from both countries have been working together in the last 4 years with experience to work towards sustainable and effective food production. And the Dutch Wageningen University and Research worked together with the Japan's Ministry of Agriculture, Fisheries, and what's the other F for? It's called MAF, Agriculture, and NERO, the National Agricultural Organization of Japan, to improve crop monitoring and management via drone technology. So it's a very interesting experiment, and well, you can find more information also on the internet about it. There's even somewhere a film where they show how they use the drones to monitor the potatoes in Japan. At SURF, we believe in open collaboration, work together, reaching out to each other, exploring new partnerships. You can scan, if you're on LinkedIn, you can scan that thing if it works. It worked on my phone, so it should. And yeah, you can connect there or come talk to me after this session or in the following days. Thank you very much. Gozaichu arigatou gozaimashita.
Thank you. So we have 1 minute left, so that we can take one question, I guess. So that if no, so that Karen will be here rest of the week. So that
so I can also answer questions at any other time.
Yes. Thank you very much.
If it's a very technical question, that would probably involve a colleague of mine to answer.
Thank you very much. So
Thank you.
The next speaker will be the Jos from the Scenic, and also from the Jonah from the Pendai GP or Pacific Wave.
Good afternoon.
There you go.
Yeah. Hi. Good afternoon. I'm Jonah Keogh. I'm the managing director of Pacific Wave, and as Sato-san mentioned, also work for Pacific Northwest Gigapop. So Josh Dickman here with me from Scenic will give a joint presentation here on both some of Scenic's internal projects as well as Pacific Wave. So we'll go over Pacific Wave, Scenic, next generation infrastructure upgrade of CalREN, which is Scenic's internal network serving Californians, some information about 400 gig ZR optic trials, and Scenic's AI resource, Scenic Air. So for Pacific Wave overview, for those of you who aren't familiar, Pacific Wave is a joint project of Scenic, Josh Works, and Pacific Northwest Gigapop, which is the US Pacific Northwest regional network in the US, and that's where I work. It's an open exchange that supports both commercial and R&E peers, and it serves 29 countries across the Pacific, connecting into the Western US, and we're supported in part by a grant from the US National Science Foundation. So I think many of you have seen this map, which is really a testament to the collaboration of the folks here in this room, and we thank all of you for the contributions to the global R&E fabric here. The Pacific Wave network operates this 400 gig backbone that you see along the West Coast, and then interconnects with the rest of the US through our shared infrastructure with Internet 2 and partnerships like NREX that we'll talk about here soon. And there's a lot of upgrades that we're working on here, and a lot of things that have come to fruition in the last 6 months or so. So we have some core pops here that I put in the slide deck, and we'll share the slides so you can go back if you're interested here. And so the key areas that I'll talk about today are telemetry work, network automation, our 400 gig upgrades, our expansion into Alaska, and partnerships, NREX and APONET. So iGrok is a flow-based traffic analysis tool that we work on with UCSD and SDSC. There are nodes deployed locally with each of the switches, which allows for a little bit different data collection compared to a centralized flow collector, and that provides us some additional insight into the network. It's also joined to the NRP Nautilus Kubernetes cluster, and we're also able to do some P4 and free router experiments leveraging that same hardware. So we also participate in AutoGoal, where we've upgraded our infrastructure a little bit internally to run everything on Kubernetes and OpenNSA. The AutoGoal framework is really important to avoid some of those long email exchanges we've all been a part of to provision VLANs. It definitely makes things go a little faster, and we are happy to continue to participate there. On the hardware infrastructure, we've replaced our MX10008 routers with new PTX 10001 36 MRs at all of our sites on the West Coast, and that allows us to enable new 400 gig connections. And we also have a full 400 gig backbone on the West Coast, connecting Seattle, Sunnyvale, and Los Angeles. And we do have some 400 gig participant connections as well online, ESNet, NAI, as was just announced in Los Angeles, and a few other folks, and there are definitely a few more coming along here. We're also looking at an expansion into Alaska, deploying a new node in Fairbanks. So this is a collaboration with MTA, who's a carrier in Alaska, and University of Alaska and Pacific Wave. We'll provide local peering connectivity initially, and hopefully, as things develop with Far North and Polar Connect and other projects, this can be a gateway for R&E into the US and Alaska. So on partnerships, NREX has been a great project. It helps connect all of the exchange operators in North America who are listed over there on the side of this slide. We have a couple of core project elements, collaboration, coordination, 400 gig interconnect, uniform provisioning standards, and measurement analysis and visualization. So we're focusing on kind of standardizing our efforts across all of the exchange operators in the US, and making it a little bit easier to interact with all of us through a uniform service infrastructure. We've seen a couple of different use cases for that, from network research, like DTN's P4, what comes next after P4, testbed development and deployment, and then transit for specific applications supporting science like SKA, NREN backup paths, and infrastructure like that. So our final kind of collaboration effort that I'm sure you're all familiar with is APONET, and we're really happy to help enable some of this backup connectivity through Pacific Wave. I know there have been a couple of examples that others have shared where link failures have resulted in no impact to customer traffic because of all the backup we provide. And increasingly, we're seeing the need for not just diversity, but triversity, where you have long duration subsea cable cuts. So that sums up my Pacific Wave overview, and I'll hand it over to Josh.
All right, thanks. So to briefly go over Scenic, so Scenic, we're the regional REN for the state of California, and one of the networks, in addition to Pacific Wave, that we operate is CalREN, which is the California Research and Education Network. We connect most public and many of the private institutes in California. Total, serving around 20 million Californians. Wasn't expecting that. So this is the CalREN backbone network. For a sense of scale, California is around the same size as Japan geographically. And so the next thing, the CalREN next-gen efforts. So around 2018, we took a look at where our network was. And at the time, we were flat IP, no MPLS, or anything that you would expect. So we couldn't do any kind of, we had very limited layer 2 support. We have a commodity internet network called DC and then a research network called HPR, and those were on completely separate infrastructures. And because of that, we could only offer the research services at, I think, 5 locations at the time. And we were also very low 100 gig support and other challenges. So we put together some goals that we wanted to accomplish. The major ones were collapse HPR and DC into the same infrastructure, add MPLS so we could do layer 2 and layer 3 VPNs and get advantages like LFA. Also expand 100 gig and then look into 400 gig offerings. High-level timeline, but we largely started this project working on the optical layer. We started refreshing our optical platforms. We had to migrate a lot of 1 and 10 gig optical services. We refreshed 14 of our backbone routers, which ended up meaning we needed to move around something like 2,000 member circuits. And then we added MPLS and all that fun stuff. At the same time, of course, COVID presented its own challenges, supply chain issues. Juniper announced some end-of-life notices for some of our hardware, which is a bit of a surprise. And then during all of this, we got a notice that our LA data center was being closed and we had to move, which was very fun. So today, in 2025, we are fully segment routed. We're able to do EVPN services over that, offering layer 2 and layer 3 VPNs. DC and HPR, we are able to put that on the same hardware. 100 gig support is basically everywhere, 400 gig support at our main locations, and then we're working on doing 800 gig right now. And this is the CalREN network right now with the red sites as the upcoming 800 gig using Juniper PTXs, which I'll mention later. So another big thing during all this was 400 gig ZR. So as we were doing this NGI project, we already had to refresh most of our routers and most of our optical transponders were going end of life, so we needed to deal with those as well. So we started planning for using 400 gig. And now that we have some of these in production, we're able to put these 400, turn up a new 400 gig circuit using pluggables at about the same cost as a 10 gig wave cost 4 or 5 years ago. So it's a huge cost savings just from the hardware perspective. And then when we look at everything else, the power, colo space, the router side hardware savings, it's a pretty huge savings. And so this is our core ring, what we call our core ring, the major CalREN locations. And we're heavily using pluggables. This project that's right here for 2x400 gig using ZR Plus pluggables will finish in a month or 2. The only spans that we can't do pluggables is LA to Sunnyvale and Sacramento to Riverside, just because the spans are too long. So there we do discrete transponders. But everywhere else is 400 gig pluggables. And even on what we call our spurs, the smaller sites, we're actually refreshing those for ACX platforms to take advantage of 400 gig. We don't need the capacity there, it's just the pluggables are so useful. And then at 5 of the locations in this first wave, we're deploying PTX 10,002s from Juniper to be able to support 800 gig connectivity. And San Diego State University will be the first one to connect to CalREN at 800 gig, and that should happen April-May timeframe. So lastly, to talk about Scenic Air. So Scenic Air is the Scenic AI resource. It's the California portion of the National Research Platform. And basically what it is a shared compute, storage, that kind of infrastructure available to the larger community. Next slide. So this is So the way the NRP works is it uses the software called Nautilus, which any student or researcher at these universities or institutes can access. You don't need to host any of these nodes to use it, but if you do host the nodes, the CPU and GPU nodes, you get preferential service for those. This is the count as of July for the Scenic Air nodes. So to access Nautilus, students and researchers don't need to do anything necessarily besides obviously connect to CalREN. But what Scenic has been doing is trying to make that easier, essentially. So we have a few different models based on the Science DMZ that everyone's probably familiar with. We have the traditional model where we connect our research and commodity traffic peerings to the campus, and then they deal with the routing on their side, or we abstract that and make it a little bit easier. So we deal with the routing. We hand off a default route to their Nautilus nodes. So it went pretty quickly, but I'd be happy to take any questions or talk afterwards, and Jonah as well.
Can you go back to that slide? There was one of the 400 gig ZR. There was 2 asterisks next to it on the backbone.
This one?
There, yeah, the in progress. Is there a reason why there's 2 asterisks there, or just because it's in progress? LA Riverside.
That's a great question. I don't know.
Okay, thanks.
It's just a picture. I couldn't edit it.
Okay, if there is no other question, because we will be installing the 400 ZR in the next week, 4x1, 4x400, so that
Nice.
it will facilitate me as well. So thank you.
Thanks.
So the next speaker will be the Sakim Jain. So that over there. You're from the Nokia and Head of Enterprise Business Development, APAC. Please start.
Good afternoon, everyone. I was a little worried when I chose the topic of next generation infrastructure. I was wondering how many people would be listening to me about how to scale the network infrastructure and optical networks. But I think I would like to thank Karen and my previous presenters, Josh and Rob. They already set the ground. They talk about optics. They talk about global connectivity. I think now we can talk about how to scale the network with efficiently, and we look at the reliability. My name is Sachin Jain, and I'm responsible for Nokia's optical business development for Asia Pacific. I'm based out in Sydney, Australia, and let's go through that. From the agenda, I'll be talking about 5 things. I'll be talking about how to scale the optical networks or how to scale the core network capacity. When we talk about scalability, I cannot neglect how do we keep the performance optimized. So we will be talking about performance. We will be talking about flexibility, because that is one thing which is very important when we talk about the network. The network has to be agile and flexible. We'll also talk about sustainability. This is a very important topic, especially for the audience that we are sitting in this room in NREN. We are not, same as commercial network, as telcos or others. So it's an important point. I'll cover it. And lastly, I'll touch upon a little bit on the reliability, which is very important when we deploy or when we implement these mission critical networks, where we are responsible for catering huge amount of traffic for universities and research and education network. So over the past decade, you would have seen the coherent optics have reduced the cost per bit significantly. So we talk about from 100 gig to 200 gig. Sorry, I'll just put my pointer here so that I can. So over the decade, you see the cost per gig has reduced significantly. We have moved from 100 gig to 200 gig to 400 gig and 800 gig. And at the same time, the speed of the wavelength and the spectral efficiency has increased, which has increased the fiber capacity by 20 times. However, if you look at the system capacity in the C-band, today we are operating very close to the Shannon limit. So the question that arises to us in front of us today is, how do we go from here to, how do we scale our network? How do we further scale our network? So where do we go from here now? So we want to cover a little bit more about how do we scale our network. We know the bandwidth is increasing significantly. We have the reports, we have the Bell Lab studies, the amount of traffic happening. And especially for the research and education network, we know in Asia Pacific, the fiber is owned primarily by the CSPs or other players. So we are using least pair of fiber to running our network. So we are not fiber rich. We don't have the liberty to keep on consuming multiple pair of fibers. So the solution that we talk about is doubling the fiber capacity by using the same pair of fiber using C plus L band. I'll go a little bit more on that one. I mean, it's a deep topic. We can go detail, but I'll keep it very high level today, and then we can have a follow-up discussion. There are different options which are people talk about in increasing the capacity. Some of the vendors in the industries are also talking about super C and super L band. However, the point here is not how much is the increase in the spectrum we are talking. We are talking about how much is the actual fiber capacity we are able to scale. I'll just take this example, a very simple example, will not go into more technical jargons and detail. If you look at the drawing here, it shows the optical fiber typical spectral attenuation. While with the super L band or super C band, you get additional 25% spectrum, but you require additional 24 transponders, all right? And if you look at here, the fiber attenuation of super L band is significantly higher compared to the traditional C band or L band. So there, you need a specialized amplifier, you need a specialized set of transponders to increase the capacity. While you get the additional spectrum of 25%, the increase in fiber capacity is only 3 to 8%. So the key metrics here is fiber usability. We need good performance over the available spectrum. We just don't need additional spectrum, we need additional capacity on the fiber. So the solution is to go with the standard C band and L band, which is available today, which is widely deployed in the industry. And economies of scale also comes into picture when you talk about standardization. So we have modular C plus L band. I mean, for network operators who want to scale the capacity on the same pair of fiber, they can just go pay as you grow. So they can start the network on the day one with the C band only, with the C band infrastructure. It is ROADMs, M-line amplifiers, and combiner splitters. To day two or later on, whenever there is an increase in capacity without burning additional pair of fibers, they can add the L band to the network. So on the same pair of fiber, they double the capacity 2 times by just adding the L band. At the same time, we are also working, and we will have very soon, integrated C plus L band for operators who really want to deploy the C plus L band from the day one itself. For examples, we heard a lot about yesterday from RNet that there are hyperscalers who are very bandwidth hungry. So they are coming to the operators asking for pair of fiber. So instead of offering pair of fiber, you can monetize your network by offering entire L band to a hyperscaler or a OTT player by a use of a spectrum sharing. Or if you have your captive requirement, which is very bandwidth hungry, you can deploy C plus L band from the day one itself. Now look at a little bit on the optimization of performance. So I have 3 animations here. I'll go quickly on that one. So what he shows is this is a comparison with respect to previous generation chipset, which is a PSC5S, which was based on 7 nanometer. Nokia last year announced a new chipset, which is based on 5 nanometer PSC6. The point here is on the same various segments on different routes, but for the same set of distances, we are able to achieve higher capacity by using latest PSC6, which is a 5 nanometer chipset. So spectral efficiency increases. However, we also keep improving the performance of the network. I'll take few examples of various field trial and press releases that we have done. And I think I just added a slide on SURF because Karen presented a little bit on the good things that they have done in SURF. So I think she missed to mention about the 800G transport trial that we did with SURF. So I could not adjust myself to add this slide. We did this with between Amsterdam to Geneva. It's using Nokia's PSC6. I'll share the slides. You can go through. These are the all press releases available. Okay, now moving on to flexibility, we want our network to be adaptive. While the bit rate and the baud rate are increasing, we see a lot of challenges in how to converge the traffic, how to map the traffic efficiently without any wastage. We see traditionally transponders, we used to have multi-rate transponders with N by multi-rate client rates mapping onto the transponder, but with huge increase in the bit rate, how do we do that? Thanks to Nokia's chip-to-chip mapping. So what we are doing, we have a chip-to-chip mapping. In the previous generation, you were extracting a 400 gigi client and mapped onto a 400 gigi line. But with the increased bit rate, where we have 600G, where we have 800G, where we have 1 tera and 1.2 tera, we are able to extract full capacity of the system, of the transponder or the card without wasting anything. And that is happening because of chip-to-chip connectivity. So what we are doing is we are reducing the number of wavelength and we are maximizing the 400 gigi client connectivity. Okay, sustainability, as I mentioned, I mean, this is something we have been talking a lot, but now I think it's time from nice to have to a must to have. We are not traditional telcos. We are sitting in this room are all research and education networks, university network. We don't commercialize our network. We don't have the same amount of capex that the telcos had. So the point here is the networks must go green. And when I say green, it's not. Today, I'm observing a lot of CIOs, CTOs in their KRA. The CEOs are asking them to make sure when they roll out the network, when they roll out the RFP, this is one of the key metrics they involve in the evaluation criteria. So what we have done here, we have done we have power saving mechanism at different layers. In your if your equipment if you have a network and you have different cards deployed in the network, and if the cards are not used, you can put those cards into the low power mode. Similarly, if there are any coherent modules available, you can automatically put them into the low power mode so that you don't consume the power, you don't require you don't have to pay the OPEX bill for that. This is an example of Nokia's coherent chipset from first generation to the latest generation. We see we have done a 90 to 95% reduction in versus the first coherent, and with respect to the previous generation, there is a reduction of a 30 to 40% power consumption. On the right side, there are a few examples of the transponders on the shelf and the total network power capacity. So you see there are significant optimization thanks to the next technology chipset we are developing, and that's how we are doing it. I mentioned about power disabled mode for the optical equipment. I mean, unused card in the network can be put in power disabled mode. So you will still be able to see the remote inventory. You will still be able to do the provisioning. It's just that the power will be saved. Once you require to turn up the card, you can, from the central NOC, from the NMS system, you can just change the mode from power disabled to enable mode. And you see that we have taken one example of a card that power saving is significant from 180 watts to 1 watt only. Similarly, line modules, they are automatically put into the low power mode when they are not in use. You still can access the inventory. You can do the firmware upgrade if you require to do any software upgrade, or you can do the temperature readings. And all this you can see centrally through your network management system. In your network management system dashboard, you are able to see how much is the power consumption. So what are the advantage of this? So you don't need to send in technician to the site to plug out the transponder. Okay, my card is not in use, so I'll just plug it out. So you don't have to truck roll. You don't have to send the technician. It can be located anytime. You are not losing your inventory. There is no loss because it's in the system. You are able to track the inventory. You don't need any additional storage to take out the card and keep it in a warehouse. There is no additional cost. And at the same time, you can just power up remotely anytime, anywhere you want to do it. Last point I just want to talk about is the reliability. This is one of the key metrics which is used. FIT is one of the key metrics which is used by the evaluation committees when we deployed the network. So with respect to the previous generation, what we have done, we have reduced it by 70%, which enables our MTTF, which is mean time to failure, is greater than 25 years. So we are constantly working on improving the reliability of the product, of the hardware, of the solution, so that there are no breakage on the networks when you deploy these kinds of network. To summarize, I mean, we are seeing 800G ultra long haul, 400G long haul up to 1.2 tera everywhere. We are seeing 400 gigi as the new currency deploying everywhere. We are scaling. We are minimizing the slots requirement. We are working on Go Green sustainability and as well as the reliability.
So does anyone have questions or no? So raise your hand if you are coming from Nokia. Okay, so these are you guys are over there, right? So that's please reach out to them. So that's yeah. Thank you. So the next speaker is also a friend of mine. So I think everyone knows Simon. So that's yeah. So he's going to present the NREN POP update. So that's
Thanks, Dr.
yeah. Great.
Okay,
Here you go.
great. So, hi everyone, I'm Simon Green from NREN. So I look after the NREN Open Exchange, which is the research and education network in Singapore. So first of all, I'll go through what we've been doing for the past 5-6 years, which is our SLIX 2.0 project, and that's funded by the government, NRF. So it kind of pertains to 3 different sections. So one of them is network, more so regarding into resiliency, setting up a new POP, new connections for our optical DWDM system, upgrades of our routers and also our backbone, server upgrades and just refreshes, and then also looking into more of the cybersecurity side of things where previously we didn't really have much traffic visibility or what was going on. So this is one of the projects was for that. And then we have the threat intelligence sharing platform and an external threat intelligence feeds. So I'll mostly be covering over the network side today. So this is our topology as of now. As you can see, there's the yellow box, which is a little bit faint on the slides, but this is where the Singapore region is. We have our main POPs in SOE1 and SOE2. So SOE1 was our original POP in Global Switch. And then for the SLIX 2.0 project, we had SOE2 pop up on the right-hand side, and that is actually hosted at Equinix SG3. So with the SLIX 2.0 project, we actually were able to achieve redundancy with our local institutes that you can see in purple, and also bringing in new international connectivity to allow for more resiliency for the international collaborations that we do work with, which I'll mention later as well. So I think the most recent connection that came in was actually BDREN coming in at 1 gig. So really great for them to be finally connected back into the NREN community after being cut off last year. So that's awesome. And actually the most recent one that should be coming up in Monday for ArenaPack is the ArenaPack link between SOE2 and SOE2 and their pop in SG1. Yeah. So I'll go quickly over what our router migration consisted of. So we used to run a big chunky Brocade MLXE8, as you can see, is one of those Serena-U systems. And it's probably lasted longer than it should have. So we actually moved over to what we call a pizza box system, or the Extreme Networks SLX 9640. So, and then you can see our port density and how we used it back then. And this is the hole that was left by the MLXE8, and then on top of it is the purple box for the SLX 9640. So it's great because we don't really have too much space at Global Switch, so we saved a lot from that. Yeah. And just a couple of feature comparisons comparing both MLXE8 and the SLX 9640. So previously we had some difficulties accepting full commercial tables, well, full internet routing tables because of the limitations that you can see there. So now we can actually accept multiple IPv4 and IPv6 tables, which is great. Larger packet buffer sizes, and also now with the SLX, we can actually perform RPKI and filtering based on RPKI statuses. And with that, it was able to allow NREN to actually join Manners finally, so that's really good. I think that was probably the main reason for not joining in the first place. We had everything ready. It's just the RPKI. That's why we wanted to actually get that sorted and completed before we actually joined. So just a brief thing. Manners is basically to ensure that everyone's kind of running their network in a secure manner, so it protects everyone and makes sure our national research and education networks are safer as is. Yeah. Also, we've been working on a backbone upgrade to 400 gig. So the reason for this is we're here to help support both on the international connectivity and then on the local side. So we are now, as of 2 weeks ago, ready for 400 gig connectivity into NREN, which is great. So the solution that we actually went with was the Arista 7050DX4. And a couple of reasons was because for, yes, the IP over WDM with the 400 gig ZR optics. And also, maybe I'll go through this slide, which indicates why we went through this. Because Arista has a optical cable coupler splitter, which acts as your mux-demux. And everything can be done in a 1RU system. So usually you would have your mux-demux as another 1RU. You have your optical amplifier as another 1RU. But with this system, they actually have the amplifiers using one of the 400 gig interfaces. So you do lose one, but it means that everything can be all set up in a 1RU form factor, which is great. They also offer another model which uses OSFP transceivers, but we're using the QSFP DD model because we want to be backwards compatible with the transceivers that we're using, which is like the QSFP 28s for 100 gig and some of the 40 gig QSFP plus. And one thing on the server side is we upgraded our database mirroring service. So this is a publicly available system, or FTP server, I should say. It's mostly hosting biological and some climate data sites. So that would be like EBI and CBI. But take note, these are only just subsets, not the full database. We would need a lot more storage for that. And if anyone in the APAN community wants to bring some of the data sets closer, just let us know. We can help to support that if need be. And following on from that, I'll just give a brief overview of the international network collaborations that we are involved in. So first of all, for the East Asia region, we are part of the East Asia Resilient Backbone Network, and thanks to all the other members and partners involved in that. That's great. Likewise, I think you will have seen this one, a couple of slides, a couple of presentations ago for the Asia-Pacific Oceanic Network, so we're part of this one as well. And then also for the Asia-Pacific Europe Ring, which helps to cover the other portion or the west side of Singapore and connectivity back to Europe. So with that, I'll just give a couple of updates of what actually happened or the outages that we actually did see last year, over the years, so from 2023 to 2025. So last year was a pretty trying year in regards to fiber cuts. So it's probably the most we've ever seen. As you can see, we've had about 13 fiber cuts and they all kind of overlap with each other. The longest ones that we did see was about 222 days. And I think what we're seeing now is that because of the lack of resources and permits, fiber cuts take a long time to recover. So we're seeing about maybe 3 to 4 months, depending on, well, yeah, depending on, on how it goes, really, yeah. So I think some of the pain points that we have learned is that there are some diversity difficulties depending on, especially on the AER side, where a lot of cables are going through the Red Sea area. Likewise, even from Singapore, and there's the Malacca Strait where a lot of them are coming into Singapore too. So it is really difficult to get really good latency and diversity because this is the easiest and most direct way to go. But the thing is, there's 3 main parts that all of these network collaborations actually do work well with. So it's diversity, redundancy, and community. So these are really important. So we want to make sure all the circuits that we have are as diverse as possible. So we might have to trade more direct paths for further paths, but at least it's diverse in that regard. We want circuits on different cable systems too. So at least if one cable system goes down, there should be another one to back it up. And another one that I think is probably the most important one is the supportive community. So this would not have been possible without pretty much everyone involved. And I think that's probably the most important aspect of these cable systems themselves. Because without the community, we wouldn't be here to help everyone else. Yeah, cool. And I think that is it from me. Thanks.
We have 4 minutes left.
4 minutes left? Oh, I was speeding through that. everything happened, really. So it wasn't really, how do you say? It's just kind of one thing happened after the other, another after the other. It was on different cable systems. It was fiber faults. It was everything. It was just kind of unexplained, really.
Bad luck.
Oh yeah, yeah, true. Bad luck is probably the best way to put it, really. Yeah, and then as you can see in even 2025, we have 4 fiber cuts that we're actually dealing with right now. So we hope that reduces back to what it was back in 2023, but this looks like it could potentially be the way forward, which is not the most optimistic outlook, but it is what we have to deal with and work with right now.
If you have solution for that.
Oh, who cut the fibers? That might be a bit tricky to go into. There's always stories of like, okay, it could be some. Yeah, it could be that. Could be anchors. Could be. Yeah, I'm not going into that.
We never know.
Can of fish. No, different fibers. Yeah, different fibers. Yeah.
But
So
similar area.
yeah, similar area. Yes, yes. Let me see if I can find the one slide. I'll just quickly bring that up. Over here. Yeah.
Oh yeah.
So this is from. Oh no, some of it's cut off. But as you can see, it's like Singapore, really.
Yeah.
Quite close by.
Did you?
Yeah. So as you can see, it's quite close to Singapore, really, which is not the best. But yeah, it is. It is unfortunately what it is.
Yeah.
Yeah.
Tropical storm, I guess. So that's, yeah. New professional answer in here.
And then basically the reason why the fiber cut is anchor of the ship. That is the most case for the submarine cable cut. So maybe around Singapore,
Everyone's.
the many ship staying the sea and it put
Breaking,
the
yeah.
anchor at that area. So some submarine affected about the anchors.
I think not surprised considering how much of a port Singapore is in that sense. Yeah.
What kind of fish do you eat?
What kind of fish? I'm not fussy. I'm not fussy. Yeah.
Oh yeah. So that's if there is no other question, so that's we're gonna move on and give him applause. So Okay, so the next speaker will be the Wayman from the I would say JUCC. Okay. Wait.
Hi, good afternoon, everyone. Welcome to the Level Engineering Workshop. I'm Waiman Zheng from JUCC, the John University's Computer Center. For those who are not too familiar with JUCC, I'm going to spend a little bit time to talk about JUCC. And JUCC was incorporated in 1970. And in the very beginning, it has only 2 universities, the Chinese University of Hong Kong and the University of Hong Kong. And it has been growing rapidly, and until now, there are 8 government universities added as full members of the JUCC and 13 affiliate members. Our goal is to promote collaboration between universities. And we have different projects like the HARLET, which was established in 1985, and the Hong Kong Access Federation, the blockchain project, etc. And the HARLET, which was established in 1985, has been developed in different phases, and now it has been growing up to a fully resilient network. It is a pretty standard network topology, and the 2 data centers are located in the Chinese University and the University of Hong Kong. As you can see, we have on the left-hand side, left top corner connect to Hong Kong Internet Exchange, which is mainly for the commodity internet. On your right-hand side, top right-hand corner, we have 100 gig link connected to Hong Kong Open Exchange, which is mainly for the R&D networks. And both of them are connected by two 100 gig link to preserve the resilience. And the university's broader router are connected to the two data center in Hong Kong U and CUHK. And as we think that we need to connect to the world, so JUCC established the Hong Kong Open Exchange in 2016. And instead of putting the Hong Kong Open Exchange in the two university data center, we choose it to put it in the Mega I. It is because in Mega I, there are a lot of R&D partners co-locate their routers there. So we can easily be connected with those partners through cross-connect and do collaboration easily. So shortly after 2016, we co-located Juniper MX 10,003 router, which support 1 gig, 10 gig, and 100 gig connection. We are located in the 10th floor of Mega I. And in the very beginning, we can easily establish bilateral peering with NREN partners like Asia Connect, NICT, SingleRAN, KiloNet, CSTNet, and CERNet, because they all have their co-location in Mega I. So a cross-connect will do the job. And we also connect with some commercial partners like AWS, Apple, and Google. And after we established the Hong Kong OX, we started move our step forward to work with NREN partners. The first one is we joined the Japan, Hong Kong, Singapore 100 gig link in 2021. And it was a collaboration. And as you can see in the two red circle, that was the 100 gig link. It goes through the submarine cable system, the TGNIA submarine cable system, which was unfortunately in 2024, cable cut in the Hong Kong Japan side and then on the Hong Kong Singapore side. And then we joined the AER, the APAN59. Also, we signed an MOU with CERNet. All happened in 2021 and 2022. And we also participate in some APNIC ISIF project. And CERNet had developed the BGP watch, and we are one of the participants. And that BGP watch had 20 partners in 19 economies. And then I think that slide had been presented by Simon before. And that is another collaboration in East Asia. And fortunately, we joined this MOU and do the collaboration. Besides the 100 gig link, the TGNIA cabling system going through from Hong Kong to Singapore, we also have another cabling system from CSTNet, the SJC. And when the cable cut in that period of time, 4 to 5 months, we still have connection to the Singapore. And so this is the highlight. As at February 2024, around the time in APAN57. So you can see we have pretty much different bilateral peering with different partners. But there is some weak points there. And it is the resilience of the different network. So after APAN57, we discussed with different NREN partners, including Intellect2, GN, Loginet, SINGREN, Arlet, and Christie. And then during that year, during the past 1 year, we had established new bilateral peering and some layer 2 circuit. And as you can see, we had established different bilateral peering with different NREN partners, including Arlet at SOE and GN at UK, and also at Amsterdam, and also Loginet at UK and Amsterdam, and also Intellect2 at Pacific Wave in Seattle. And this is a diagram that we want to establish. As you can see in different bilateral peering, the bracket one is the different summary cable that we try to make use of. You can see that the frequent cable cut is in the Red Sea area. So we try to establish 2 different cabling systems. Hopefully, it won't be cut at the same time. If it is cut at the same time, then we still have a backup path going through the Pacific Ocean to the Intellect2, and Intellect2 will deliver the route of Europe to us. So this is a traffic pattern we have last year. Although there are 13 cable cuts, our network is fully resilient and didn't really been affected by the cable cuts last year. And besides network resilience, we also set up different monitoring or measurement tools, including the Persona. We also engage some DDoS mitigation platform to protect our network infrastructure, the Harlet network infrastructure. This is an on-demand service. If there is a DDoS attack and the traffic, the DDoS mitigation platform will announce a more specific route to the internet. So that kind of malicious traffic will go through the mitigation platform and the scrapping center, and then clean the traffic and transit back to the JUCC institutions. About the upcoming plan of Harlet and Hong Kong Open Exchange. In the last diagram, in this diagram, we have a pretty robust infrastructure to connect to the Europe. However, in the Pacific side, Pacific Ocean side, we have only one bilateral peering with Intellect2 in Seattle. So we are trying to see whether we can establish more bilateral peering. This is the only one, the Trans-Pacific bilateral peering. We are discussing with, we have meeting with Intellect2 later today, tomorrow. And also with different NREN partners like SINGREN or Arlet to see whether we can leverage the rich topology and set up different bilateral peering in Los Angeles or Chicago. And besides, we would like to increase our BGP security by joining Manus. We have checked that we satisfy most of the mandatory action required by Manus, and we will upgrade the Hong Kong OX router later. And this is the Hong Kong OX readiness. We are trying to join the Manus, but we are still working on the RPKI because JUCC is the APAN59 member and acquired 2 Class B address, which have been distributed to the 8 universities. So we need to clarify whether those IP addresses are portable IP address before we can implement the RPKI. And this is the readiness of Harlet, same as Hong Kong Weeks. And lastly, I want to talk about the Harlet projects. And I borrowed this from NREN. Yeah. And NREN had established a layer 2 link from organization to the SCON, the next generation test bed. I think they are using VXLAN. And one of our universities, City University, also want to connect to the SCON and do the next internet architecture test bed. And we are trying to set up the layer 2 VLAN for them so that they can connect directly to the Hong Kong edge device. This is the first project. And the second one is by the Chinese University of Hong Kong. They have the Large Hadron Collider cooperation. They are the tier 2 partners of Large Hadron Collider. And we are seeing whether there is something more we can do. But we need to discuss with the researcher first. And the third project is from the University of Hong Kong. And it's about data analysis to increase the image of the astronomical data through deep learning. They are using a method called Monte Carlo method. And there are a lot of data, 30 terabyte data transfer from Spring to Hong Kong U. And this is the last project I want to talk about. The University of Science and Technology had deployed an immersion technology for HPC, which, if you see the link, it is published in their website. And I think with the open exchange network, they can easily be connected to other institutions and doing the research together. I think that's about all I present today. And thank you very much.
Thank you. I think I can take one or two questions, or if not,
Yeah.
yes.
Yeah. Thank you.
Thank you very much.
Yeah, thank you.
I hope you will be hosting a good APAN60 meeting. So
Yeah, yeah. We have actually had a lot of colleagues coming to APAN59. Yeah, if you see someone wear this hoodie, who will be coming from the JUCC. Yeah, thank you very much.
So the last presentation is from my colleagues. So and Shogo Yoshoka and Kodai Motohashi and Chenshi, of course.
So hello everyone, we are APAN-JP NOC, and today from the APAN-JP we have 3 topics to speak. And for me, I will be sharing the APAN-JP network operation with many collaborators in APONET. So, I'm Chenshi Sun. Yeah. So this is an APAN-JP backbone. APAN-JP has multiple backup links, and the main path is the link colored in red, and it is the NREN JUCC and SIG links, the colored in red. And for backup paths, there are 4 paths. And in last year, and on 2024, as Wyman mentioned, we have a very big outages in the JP Hong Kong and the Hong Kong Singapore link. And especially for JP Hong Kong link, the outage was lasted for 178 days. And also, there were the time that JP Hong Kong link and Hong Kong Singapore link outage happened in the same times. However, the availability of the JP backbone was 100%. So that is because there is a many backup paths that the APAN backbone can bypass. So thanks for all member again that providing for backup paths. So besides the APAN backbone main link, so here is a link availability rate around Asia. And as you know, submarine cable is very important because 99% of international communication is achieved by submarine cables. However, because of many reasons, it is difficult to maintain link availability above 95%. So mutual cooperation between organizations is very important for us. So since it is hard to keep link availability above the 95%. So I tried to figure out from APANet's last year data to know what is causing the drop availability. So this is in APANet there was a total of 19 significant incidents in last year. And they are categorized into 3 main types: fiber cuts, maintenance, and fault. And here we have a list of the major outage and disruptions. And I highlighted a key incident which the duration was very, very long. And all of the events that I highlighted is all happened in the summary section. And come to this slide, the same slide that Simon shows. So I plotted the body points, and yes, there, the body points around Singapore is, yeah, there's a many fault points in Singapore. Yes, and so, and a little in Taiwan and Philippines. So that was just an example of the data uses. But I would like to say that sharing information each other, and through the information, we can reveal points of the weakness. And it will be helpful to strategically create a future network plan. So each community is increasing its resiliency and redundancy by backing up each other, as Simon and Jonas mentioned. But of course, I know, and it is very, very important, but I think we need to considering for strategically creating a future network plan across all R&D network as well. So that's all from me. So next.
Okay, hello everyone, I'm Kodai Motohashi. And next I will talk about the updates on the SR segment routing MPLS implementation for the APAN backbone. And at first, actually I've been working for over 1 year about this project, and I will briefly explain the motivation for implementing SRMPLS and the benefit. And in recent years, we have focused on improving fault tolerance and availability. And as a result, isolated outage rarely occur at the site with multiple paths. And therefore, as a further improvement, we are working on the realization of flexible traffic engineering based on new various needs. And so we are now introducing SRMPLS into APAN backbone. Next is the overview of segment routing. And segment routing is a source routing method to represent network as segments. Segments define the actions performed on the packets, and the segment list was encoded by in the packet by the send nodes. And the traffic engineering methods on the SRMPLS backbone are not limited to specifying the segment ID. One of the good features of the SR backbone is Flex Algo. Flex Algo offers several methods for route optimization, and you can decide which routers and links are allowed to pass through over the link. And flexible traffic engineering can be achieved by applying appropriate flex algo to each routing instance or VRF. This is a summary of the new things that can be with SRMPS backbone, and the new SRMP backbone enables more flexible traffic engineering such as latency, bandwidth, and etc. And it also enables source routing and layer 2 VPN and layer 3 VPN, and additionally automatical fast rerouting TILFA. These are the progress of construction. At the time of the presentation in APAN58, we have completed the layer 2 and layer 3 VPN testing in the production environment. And then we finally completed to verify network requirements and design and to deploy the SRMPS backbone and completely migrate the traffic from the current backbone, old backbone to new one. And it is done in this mid-February. If you can see any problems on the traffic through APAN-JP since the mid-February, please contact me. Yeah, I hope there's nothing wrong. And then, this is our environment, and our all router Juniper MX3s and ISIS is used as IGP. And we are using only private IPv4 for the ISIS and the IBGP. And actually, the Wi-Fi for the internet access here, and I mean SSID APAN59 is passing through our new backbone. So your internet reachability shows our backbone, new backbone is working well. That is all from me about introducing SRMPS into our backbone, and thank you for listening.
Hello, this is Shogo Yoshoka. The next, last APAN-JP update is regarding Persona. APAN-JP has been involved in the development and deployment of the Persona project since its inception. Deploy some hosts for measurement and management. And through various activities, we have contributed to its deployment in research and education network in Asia region. In this room, maybe, as you know, super leadership with our boss, Ikeda-san. Yeah. And in recent years, we have comparing performance measurement between GXPs. At GNG website, you can see this GXP map dash. Next, in today's update, I would like to talk about the upgrading of 100G testing hosts and management hosts with the latest Persona version 5 and Grafana-based system. And I also would like to talk about restarting the display network measurement results between GXPs between APAN nodes. This is about 100G nodes update. With the start of supporting Ubuntu 22, we have selected the OS and migrated from CentOS. Regarding the node specifications, we built using ESNet 100G node implementation design as a reference. And next, central management hosts. Selected OS is same. On this server, we managed PS configs and compared the measurement results in Grafana dashboards, named GNA dashboards and APAN dashboards. GNA dashboard status is here. The target nodes being measured are listed on the right nodes. Some hosts are in the process of troubleshooting, and others are scheduled to upgrading, I heard. For example, Pacific Web and Netherite. So Anyway, thank you for supporting to display the measurement data. And next, APAN dashboard status is here. The target nodes are listed on the right. So many APAN nodes. But as you can see, we are still in the process of restarting measurement among these nodes. So we are going to work with APAN and GXPs to get visualization network management. I think this could be achieved without the cooperation of your NRENs. In this room, I would like to say thank you, Shingaran Simon and JCC KWFON, Taren, and Pacific Web Transpac. Also, we are concerned about active monitoring through Grafana visualization. We would like to be able to be notified when there is a sudden drop in performance or missing measurement data. So there are many supports in the visualization. Thank you for all NRENs, and thank you for continued support. That's all.
We have 5 minutes left. And thank you for the super efficient time saving.
Sorry.
Are there any questions? So we had the super busy February along with the silent upgrade. So that's So if not, this is the end of this session, and we'll be having another network engineering session in 30 minutes. So please do pick up your drinks and come back. Thank you very much.
Okay, everyone, we're right on time. Francis has asked me to chair this network engineering session. So we've got an action-packed lineup of speakers. Could I invite Stephen Schroeder from Benox to start presentation, please?
Yeah, thanks for having me here. I'm Stefan Schroeder from Benox. Benox is a spin-off of Deutsche Telekom, and we focus on flow analytics. Well, being a spin-off of DT, we obviously come from Germany, so it's been quite a journey, and I'm happy to be here. I just want you to show how flow analytics actually look in action. So we have a couple of screenshots also from your NREN partner networks. So we are happy to be active in SurfNL network and also in Nordonet. And we also have an installation in Jean's network, and they helped us to develop a feature which I can also show to distinguish VRFs in the network. Good. So actually, why collecting all that flow, making all that massive data available? So what's the purpose of that? We also serve commercial networks, but I think the challenges are pretty similar. So by really understanding your traffic, you can actually better steer and optimize the routing, the transit. Actually, knowing all of that also enables you to set up peerings, optimize the peerings, and also the relationships to your customers, or in your case, the members. Also, getting your capacity planning right helps a lot if you know what's in the pipe and not only how full the pipe is. And debugging problems quickly also, it helps a lot understanding the traffic in your network. All of that leads to reduction in CapEx and OpEx, better quality of experience, quality of service, and yeah, just more efficiency in your operational team. Good. Then how we do that? Well, obviously, the most important data point you need to collect is net flow in whatever flavor, SFlow, JPFix, NetStream, whatever your network exports. But that alone doesn't tell you too much. So what we do is actually we also collect anything a router talks natively. We would have BGP connection, an ISIS connection, or OSPF, then also collect SNMP or telemetry, and even a dash of DNS. And with all of that together, we actually put that all together, correlate it. That's a bit of a challenge because of the massive amount of data being held here. And then we actually display all that information in different pages, depending on the use cases you want to have supported there. So that is an example screen of how it looks like in the end. So what you see in the top is a send key diagram. That helps a lot to get an overview of the traffic profiles you have in your network. It's probably a bit small print to see it from the back. So I just explain you a bit on the dimensions here. So we always follow the traffic from the source to the destination. So on the left, you would have the source networks, which originate the traffic. Then the next column would be what we call handover networks. So these are transit providers, peers, your member networks, whoever is directly connected to you. Then the next column is ingress routers. So these are the routers which first see the traffic. They can be PEs or border routers, wherever you have connected somebody. Then we even have two columns in between. That is a potential link in your network. So any link in your backbone, even if it's just between two LSRs, that could be a wet segment, a subsea cable segment in your network, can actually also be displayed and filtered here. And then we follow the traffic through the egress router, then the next hop AS, which is again a directly connected network, and ultimately the destination. And you can actually easily see how the traffic distributes. Without a filter applied, you always see all that traffic, but you can actually filter your way down to whatever you want to see. Just right-click on any of the items and say, I want to add it to the filter, or I want to exclude it and see everything else. Then below, where we have the 3 here, that's the time series to actually break down any of the dimensions over time. And then we list a couple of KPIs here, like 95th values, maximum values, averages, and the like. We also do overlay SNMP. You see that here in this little example in the middle, because very often routers fail to export flow like they should. And actually having a real bit count measurement overlaid on top of that immediately spots you where you might actually have data errors in the system. We also have, for more detail, what we call the raw network analyzer. That comes with a bit less history, but here we have the entire data model available to you, up to 30 data points. That would include prefixes, protocols, port numbers for both source and destination, and everything you could imagine, including BGP communities and everything. And you can filter by that, display it, group it, whatever. So that actually is, in a summary, what we do and how we do it. And now I have one use case which Surf happily allowed us to share with you. So that was actually, once we got installed, really just days after, they just stumbled over the fact that, well, they had a pretty new transit provider those days. And what they didn't know was that Akamai or CDN's traffic was actually coming direct or indirect for nearly half of the traffic here, although they had a direct interconnect. So that obviously shouldn't be that way, because transit traffic is expensive and just adds another hop. But they were just totally unaware of that. Well, with that tool, it immediately got into their face. And so they talked to Akamai and changed the BGP announcements a bit. And then just a few days later, that was actually the result here. So obviously, it's pretty easy to get all of that traffic direct. Well, for that CDN, they have quite some cache fill, so that was the remaining yellow parts here. That's actually traffic coming via an internet exchange, because that cache fill couldn't come on the directs. But that immediately helped them to lower their transit bill and also increase the quality there. We have a couple of other use cases where I can just display how they look like. So this here, this is the one which Jeant really helped us to get developed. While working with the NRENs, we realized that NRENs tend to split their traffic in VRFs heavily. So that seems to be Well, in commercial operators, that's also the case, but typically they are mainly interested in understanding their internet traffic. But for your NRENs, VRFs are really a very important element for the different traffic domains you support. And therefore, we had the challenge to also be able to add that as a dimension, which then can be filtered by or displayed. And as I described, we use BGP to distinguish the entire forward path of the traffic. So really having an end-to-end journey of that traffic from the source to the destination. And in VRFs, obviously, you would have a totally different BGP table to apply to a specific flow. So that actually was a bit of the challenge, not necessarily to get the data model together, but really make that scalable. So we talk in our largest deployments, we currently collect about 100 billion data lines a day just in flow. And we are augmenting that with the BGP information. So actually getting that done at scale was a challenge we had to cover here. We've been successful, so that's actually the outcome of it. And now you would be able to distinguish your traffic by VRFs easily here. Also things which happen in real life here are just traffic drops, very sudden changes. That could be a member of you who also has another transit and moving traffic away, or even more severe, actually traffic which is destined to, well, end users, which all of a sudden disappears, and then that would be service affecting. We even have alerting systems there, which learn with machine learning, learn usual behavior of a specific metric. And they would actually trigger, even without setting a threshold. They would just tell you, okay, this is an anomaly, and you probably want to have a look at it. And then we have pages for special purpose. So this is a heat map for capacity planning. As you can see, there were a couple of interfaces connecting to Vienna routers here. All of them have been pretty busy. And then they've been upgraded. So you see that indicated here with the blue lines. And after that upgrade, obviously the utilization levels came into normal again. But if you wanted to look, for instance, at the second line, what is still on it, why is that still so heavily utilized? That is actually, instead of just measuring the pressure of a link, you can also just see what's in it and really just filter on that specific Vienna backbone link. And yeah, with that data set, you can, I typically say, if you have a pipe system, like network links and capacity, it's a bit comparable to a water pipe system. So what you typically measure with SNMP is pressure and throughput, and we bring color to the water. So at any point in your network, you can just look at it, inspect it, and say, who has sent that traffic, how did it enter, or where did it enter my network, where does it leave, and even with a DNS grain of information, even say which applications are in it. Yeah, that's in a nutshell what we do here and what can be done, also supporting your NREN networks here. And just reach out anytime if that is interesting. And then arigato. Thank you. No questions?
Any questions from our online audience? Looks like you're off the hook. Okay, our next speaker is Edwards, PI of Transpac 5, presenting on the Transpac 5 project, evolution, impact, and future directions. Over to you, Ed. While Ed's getting set up, presenters, if I could get a copy of your PowerPoint presentation. I've got a thumb drive up the front, or you can email it to me.
My full name is, in fact, Ed Moynihan. From Indiana University in the US. I'm the Director of International Networks at IU and also the Principal Investigator of the Transpac 5 project. Happy to be at APAN59 to give the update on the project. Since it is APAN59, I believe this is the 59th time that Transpac has given an update to this audience at APAN. And we're happy to be here and hopefully to reach the milestone of 60 later this year. I'm going to talk a little bit about the current state of the project and also about how we see the project evolving into the future. But I always like to start with a little bit of context about Transpac and our relationship and involvement with the APAN community. I've shown this slide before. This shows the nearly 30 years of collaboration between Transpac International Networks at Indiana University and this community. I believe Shinji gave a keynote in Islamabad at APAN58 that touched on a little bit of this history about the founding of APAN and how it aligned with the very first Transpac proposal to the NSF in 1996, which also coincides with the founding of Internet 2 in the US, which then triggered the creation of, or the recognition for the need of an Asia-Pacific regional network to coincide with the proposal to the NSF in 1997 that was then, that led to the creation of APAN, and then that proposal was that was funded in 1998 as Transpac. And you can see there the 5 iterations of the project and the capacity that each one of those projects offered in support of research and science collaborations between the US and the Asia-Pacific region. So yeah, Transpac 5 is where we are today. A little bit of an overview of that project, still funded by the NSF as part of the International Research Networks Connections Program. We still primarily operate lease capacity right now, 100 gig between Seattle and Tokyo, part of a consortium with partners on 100 gig lease circuit between Guam and NREN, Singapore. And of course, a partner, founding partner of the APONET consortium. But we don't just operate circuits, we also provide services to the community, measurement and monitoring tools, like NetSage, which I'll talk a little bit about later, dedicated support for experimentation and network research, and dedicated science engagement and end-to-end performance improvement in science communities. That's the core of the funded activities of the project. And maps, of course, to show our 2 links, and then how they fit into the rest of APONET. So we have 2 contributions to the larger consortium. I did notice that this map was done in 2021, so it's a 4-year-old map, and I think it's still accurate. There may be some changes coming, but 4 years going, this is still, capacity has changed, I think, on some of these links, but the overall architecture, I believe, remains the same. So those are the circuits. Measurement and monitoring. As I mentioned NetSage, we've presented NetSage here for many years. This was also a funded project that our team had to develop a measurement monitoring tool for the NSF-funded links. It has since expanded and provided measurement tools to a lot of research networks in the US and internationally. The project ended at Indiana University almost 3 years ago. So we're currently maintaining NetSage for the international links, but there's no longer development happening at Indiana University. So we provide NetSage to APONET and the Transpac project, but we're putting our resources into a new consortium that is based off of the PerfSonar model called Metronova. It's a partnership organization that includes ESNet and Internet 2, TAC in the US, University of Michigan. I think it's open to other contributors that's trying to develop some standardization around measurement tools in the US. So this we see as the next generation of measurement monitoring tools, and we treat it like a research project. So we're investing in that development, and we hope to transition from NetSage to some of the tools recommended by Metronova over the next few years. We've also invested in traffic projections, volume projections in the Pacific and the Atlantic as well. We're working with partners and the global NOC to develop a methodology that could be standardized. We're working with science projects to understand the increase of their data flows, and trying to produce a report that will allow us to look out, look out 5 years, 10 years, 20 years at expected data volumes across the ocean. This is a screenshot of the NetSage dashboard for APONET. Shows you the breadth of what we can see across the entire system. You can dig down a little bit deeper here and see some of the flow data. Another screenshot that just shows you sampled flow data, top sources by volume and by rate. It's open, netsage.global. Anybody can go, anybody can see the traffic that's moving across the entirety of APONET. Let's see. Point out here, however, I took this screenshot, I hate to admit, this morning when I was doing my slides, and you can see the average usage across all of APONET links. They're all 100 gig, now 400 gig. SciNet has a 400 gig link just recently. 3.19 gigs is the average utilization across all of APONET. Other focus areas within Transpac, as I said, network research and experimentation support. That includes support for NSF-funded projects, other experiments. We work closely with the NRP and the GRP globally, and the APRP, which also is having, I think, a meeting right now, so we're missing that. We lead the SciNet NRE team. I suppose I should say we led it last year. I don't think we're leading it again this year, but Brenna was the chair of the SciNet group last year. And we've been working to do some integration of LeoSat. So we've been experimenting with essentially residential Starlink terminals and deploying them in remote regions and doing some testing to see how we can integrate LEO into the existing networks. End-to-end performance, of course. We chair the APONET engineering group, participate in NAREX. Brenna is the chair of the GNA APAN routing working group to look at improving routing performance. And we try to embed ourselves in our user science communities to better understand their needs. LHC, SKA, we saw a talk yesterday about SKA, NIH, other US-funded entities. I do have a use case here, if I have time, that is a project that our team has been working with partners on improving network performance for the Event Horizon Telescope, which is an array of, I think, 11 telescopes across the world that uses VLBI. Event Horizon was responsible for the picture you see there, this kind of blurry picture of a black hole. The first ever picture of a black hole, I believe, is 2019 when this was released. There was a corresponding picture to this in the media of the scientists standing next to a huge stack of hard drives that they had shipped from the telescopes to the MIT Observatory in order to make this photograph. And our community should be shocked by that, to see all of those disks shipped there. So we set off 5 years ago to see if we could figure out why they were shipping disks and to see if our community might be able to support them via the RNE networks. And it's evolving. We ran a demonstration at SC24 in November where we were using the RNE networks to help with the collation of the pre-check process of the telescopes. So this allowed, so that the astronomers have a set amount of time on the telescopes. And if they take a chunk of that time to calibrate the telescope, that takes away time that they're actually putting towards the observations of the sky. And so we were able to do a test run that allowed that pre-check process to be done before the actual science to make sure that there was no lag between the telescopes taking observations. So this is a small step. Partially the reason why you can't solve this problem for all of the telescopes is because They're in extremely remote places. One's at the South Pole, and one's on Greenland. So there's no connectivity at all, so thus the shipping of the disks. But we did some testing and worked with our European colleagues a few years ago to upgrade, and it eventually led to the upgrade of the links on the mountain to the telescope from 1 gig to 10 gig. So it's slowly but surely, we're going to be doing some more testing this year with real data and hopefully presenting on this, the success of this throughout the rest of the year. So just an example, a use case of the type of engagement work that we do in the science communities. Okay, so some updates on Transpac for since the last APAN. We're continuing support for the circuits, operationally stable. We are removing our router, so we're working with our colleagues at PacWave to remove the router that's been there for 10 years, I believe. We're removing it on March 17th. We've worked with all of our peers and moved them over directly to the PacWave router in Seattle. This will take out a hop in the path and should help with round trip time, with performance across Transpac. And we're also hoping, so we'll get rid of that router, and we're also hoping to plug into the exchange point, the new GXP in Tokyo when this comes online later this year. I mentioned the measurement and monitoring, so we hope to transition from NetSage slowly over to Metronova to offer more capabilities in measurement and monitoring, continued science support, targeted science support. And we're also sitting on 25 years of international science data at IU and the global NOC. And there's been some interest in taking a look at that data, seeing if we can transform it, and potentially making it available to the community for research. So we're looking at working with the NOC to do that. So again, I'll return to kind of finish here, return to this slide, the context slide. We're in the 5th iteration of Transpac. The project's going to continue. The initial funding was for a 5-year period, 2020 to 2025. But we are continuing Transpac now indefinitely for the future. We do have additional funding within the current project to extend operations as they are. So we have a little bit of time to understand what we're going to do next. And we've had a lot of conversations last year and this week about what does that look like? What does the continued partnership between Transpac and the APAN community look like? And I've got a few questions here and a few bullets. So Transpac will continue. We're here. We're not going away. We'll continue to provide the services that we've provided since 1996. But our funding models, the policies, priorities, and the science needs are changing, and they sort of always have over the last 30 years. So I decided to go back and look and see if I could look at the previous projects and the previous collaborations and find some sort of lessons from the past 30 years and try to apply them to the future to see if we could learn how to adapt to some of the changing realities today. And so an open question is, again, how can IU and how can the US R&E community work with APAN to ensure sustainability of Transpac or other projects, and to meet the needs of our users. And I pulled out just a few bullets that I'll run over. And I think these are specifically opinions of a small research team. We're not an NREN. Things that we have learned and things that we like to apply to our future work in this community. So we have to make sure that any investments we make are aligned with several priorities and needs. So those are the needs of the science community. Do we really know what our science community needs in terms of networking? I'm not sure we do. Where are we learning about the engineering needs? I think we utilize the APONET engineering group to look at architectural needs and engineering needs. And any future investments that Transpac will make need to be aligned and need to be agreed upon within that group, prior to any sort of proposal for funding. We need to adapt to the changing priorities nationally and internationally. We have to prove that the ROI. We have to prove there's a return on these investments. What impact do these projects really have? What metrics do we use to judge the success of production networks? I don't know. Is it traffic levels? Is it traffic volumes on our link? Is that the right metric? Is it number of resilient paths and backups? Maybe. Is it support for science? How do we measure our science impact? And once we do that, how do we communicate that? Is it via websites? Is it in the field? I think we have to get better at understanding impact, quantifying impact, and communicating it. We're going to have to diversify funding. We've been funded historically primarily by NSF, but also by USAID, NIH, and other US agencies. We're going to need to look for additional sources of funding, better engagement with industry, and new funding models. Of course, we've started looking at cross-border investments with, for example, the Singapore-Guam Consortium, co-funded links in ANA and APONET. These are going to become essential for future investments. And we have to continue to develop and maintain truly trusted partnerships and collaborations. These need to be active and meaningful. We have a tendency in our community to rush to create new groups, new partnerships, but we're not very good at measuring their success, again, in my opinion, and sunsetting them when they need to be sunset. And I believe that these partnerships and collaborations need to be transparent and open. We need to resist the urge to, although we do work in a competitive research environment, we have to resist the urge to be competitive, to fight for traffic, to information gate. If people want to partner, we should be open to that and transparent. And I'll end by saying that science collaboration is truly a diplomatic bridge. And I think we're lucky and uniquely positioned in that we support science collaborations via technology, but we also do science. We also do research. So I think we're unique in that sense and have an opportunity to do technology diplomacy in spaces like APAN. And on behalf of Transpac, I look forward to doing that over the next few years of Transpac 5 and into Transpac 6. So.
Thanks, Ed. Our next presenter is, excuse me if I bungle your name, Yesawini from Head of Operations of REANS, Threat Blocking at the Network, Border and DNS Services. Over to you.
It says I can't share.
All good, we're seeing you fine.
Let me just start the sharing. All right, thank you. Thanks, Yuman. I'm Yesh, Head of Network Operations at REANS. Sorry I couldn't be there in person, but hoping to see you all in New Zealand for APAN62. And today I'll be talking about a cool project we did last year and the year before, threat blocking at the network border. This is the REANS network. REANS is New Zealand's NREN. We have 100 gig backbones across the country, and we are connected to the rest of the world via the Hawaii subsea capacity to Australia and US. We are part of the APONET consortium, and our members are universities, CRIs, and independent research organizations and politics in New Zealand. A couple of years ago, in 2023, there was a challenge thrown at us. It was our members asked us, can we block the cybersecurity threats at the network level? In the same breath, the government directed all state sector agencies, including REANs, to adopt some of the cybersecurity threats into their IT environment. So we wanted to first look at the threats and see if we can take up the challenge. So we looked at a couple of government agency threats. The first one is the National Cybersecurity Center's malware-free network threat. It covers a broad range of threats to the country. And the second one was CERT-NZ phishing disruption service. And as the name indicates, it's mostly focused on phishing disruptions. These threats are formed by these agencies using local knowledge for New Zealand and international threat intelligence like the Five Eyes. But both of these organizations create threat intelligence that is very relevant for New Zealand organizations. And that is what makes these unique and relevant for both REANs and its members. These threats come in form of three formats: IP addresses, fully qualified domain names, and URLs. While we know the fully qualified domain names and URLs are processed at a higher layer of the network, we decided to focus on IP addresses in the first go. So the first thing to figure out was, how do we consume the feeds? So we partnered with a company called Cassini. They were government approved, and they just made the consumption of the threads using APIs and making it faster and easier for us. So we've partnered with them. They also assist in sending telemetry back to the agencies and anonymizing the data. So it solved that problem. And then we had a couple of challenges on like trying to block the IP addresses or these threat indicators at the network border. The first is the list changed frequently. It's about 10 minutes. The list changed frequently, and we needed timely mitigation. To know that there is no point in mitigating later on, so we wanted it to be dynamic in nature so that routers can block in real time. It was not enough to simply block the threats. We had to send the feedback back to the provider in an anonymized format and or an expanded format. Fortunately, both of this can be solved using BGP flow spec, which is basically an ACL that can be distributed to the routers. The most common use case that you all probably use of BGP flow spec is DDoS mitigation. We use it pretty similar way. You can see our flow diagram here. The feed providers, we consume the indicators using APIs frequently. That list is then ingested into Go BGPD. And the Go BGPD daemon distributes the ACLs via BGP flow spec to the REAN's border routers, which blocks the traffic, and the back traffic is redirected to a telemetry engine. And the telemetry engine generates a JFlow record, which is used for telemetry back to the feed provider. We also send logs to collect the logs of blocks and expose it to our members via member portal of what got blocked for them if there is a troubleshooting requirement. We could have used logs instead of JFlow, but we saw a problem with scale and we stuck to JFlow, and that's worked well. So this is our workflow, and it's been working since it was deployed in June 2023. So what really got blocked? You'll be surprised because we're blocking at the network layer. Since June 2023, we've blocked about 4 million blocks. So I did this presentation at TNC. At that point of time, it was 5 million, but it's now 400 million blocks that has happened till date. Some of the graphs here, most of the IP address blocks are remote scanning that gets blocked, and some malware activity. And the right side, the graph shows us that it has the number of disruptions we do in 5 minutes. It averages about 5 to 10K in every 5 minutes. These are some of the malware families that's gotten blocked. In 2024, we also integrated the threads into the DNS. So as you remember, there was one more format, which is DNS. And so we integrated that in a similar way to our recursive name service that we provide to our members, and used RPZ zone file transfers to block these threat indicators. Works pretty similarly. We, again, feedback telemetry sent back to the provider and logs of blockage sent to the members. Again, this has been active for about 8 months now, and it's been well received by our members. This is the categories. As you can imagine with DNS, the majority of the activities are malware activity that gets blocked, and phishing gets blocked. So about 75% in the last week has been malware activity, and about 25% with phishing. The next thing we are going to work on is IPv6. So the IP address blocking was only for IPv4 till now, but we now have IPv6 blocking or threat indicators going to be made available soon. So we are going to start looking at how to integrate that into our network. All of these projects have had some lessons learned, and it was good to share. We've had a brief analysis, and what we found was blocking was the easy part of the implementation. We thought that would be hard. Excluding well-known addresses as a safety net is a good thing to do. So, it's just to make sure if there is something that goes wrong because we are blocking at the network layer, we want to make sure that the basic services are still up. Telemetry was the hard part of the implementation, especially because we needed consent of the members for expanded telemetry to be sent back, and that added complexity in the code and the processes that we had to build around it. Opting out is hard. So this is a basic service that every member of REANS gets. And if they want to opt out, it's hard because BGP flow spec on the routers favors one direction. We still need endpoint protection. So this is not about replacing any of the security solutions. This is about adding defense in depth. So we still need endpoint security for remote workers or people moving around. And collaborating with external parties enabled us to move quickly because we did not focus on how to consume the feeds, but what to do with the feeds, and partnered with somebody else. Very short presentation. I'm happy to take questions. Yeah.
Are you collaborating with ARNet folks on their SOC?
Not yet, no.
Thank you very much then.
Thank you, Andrew.
So I'm Andrew Howard, Associate Director, Cloud Services and Innovation at National Computational Infrastructure. Although I wear many hats, I'm a long-term network engineer, and I'm acting as Chief Judge of the International Data Mover Challenge. I'd like to start with an introduction and then move on to what the Data Mover Challenge is. So the Data Mover Challenge is an event held typically every 2 years. We've been in hiatus for a year or two. The rationale was twofold. Firstly, to identify new and better methods of data transfer, looking at different toolkits, different methodologies. To identify emerging network tuning parameters, things like different congestion control mechanisms, I think how BBR operates, how Cubic operates, how Quick operates. But most importantly, to build a relationship and trust that we have developed between ourselves over the last 30 years of network engineering, creating all of the networks which connect us together. That relationship allows us to know that if somebody actually raises a question or an issue, they do actually understand what they're talking about. And you don't need to kind of do the level 1 triaging. You're able to directly go to the issue. So we'd started to observe that the younger network engineers were working in isolation. Typically, it's kind of the more senior people who come to events like this. But we need to bring the younger, newer network engineers in and build up that trust and capability level. And we thought the best way to do that was to actually pose them an operational challenge using our production RNA networks. Like all other aspects of our networking, it's all about data. Our high-performance networks are absolutely the key to data sharing, both nationally and internationally. We need to look at fair and care principles. NCI and our NRENs typically do not impose any ingress or egress data charges, unlike the commercial hyperscalers. And most importantly, we wanted to move to a capability of friction-free data movement. Researchers just want to access their data. They don't have time or the interest in becoming network engineers. That's our job. We've been working on this for years, so it should be just easy for them to use it. We also wanted to have a rich range of tools built into containerized toolkits that could be deployed easily at DTNs around the world. So we have known operational toolkit capability that can be easily instantiated. In these days of combinative science, where we're looking at combining satellites, telescopes, sensors, Internet of Things, ultra-high definition images, genome sequences, and external data sources from around the world, we've got a diverse mix of data products that we are moving around that our networks are the underlying and key capability that our scientific communities use to communicate. Just to put this into context, and I know we all know about this map, but the global internet is a complex, multifaceted, multi-decadal system that continues to evolve and change. Australia, being pretty much the furthest away from anywhere else in the network, requires specific network tuning to ensure that the data flows operate correctly. As part of the Data Mover Challenge, identifying that best case or the best scenario for tuning, I've got a more vested interest in making sure that our scientists and our researchers are able to access the highly expensive resources that we've thrown into these networks over the years. So the International Data Mover Challenge typically operates every 2 years to identify best practices for systems, networks, tools for large data transfers. While it can be considered as just a DTN to DTN operation, the underlying the connected parallel file systems, I/O and storage methodologies also play a key part in it. As I said, we aim to bring together networks from industry and academia in a bid to test their software and solutions for transferring huge amounts of research data. When we started, we were using a VLAN-based system and isolating it from the production network flow. What we found with that is some bizarrely complex troubleshooting requirements. Operating VLANs is all fine, provided there's traffic running over it continuously. Some of the issues we encountered were ARP aging that would not automatically recover, requiring circuit teardown and re-establishment. This was all manually set up, not using something like AutoGoal, which is doing periodic pings, which keeps those links alive. So in the later iterations, we decided to switch to operating over our production RNA networks. That has the advantage of giving the network engineers observability of the data flows and the capability to actually participate. And as I mentioned, this is absolutely critical for Australian network operations. Working for one of our 2 Tier 1 supercomputer facilities, we really need to have that data flow capability. One of the projects that I work on is the Copernicus project. That delivers 16 terabytes of data every day. It never stops, and there's no going back to kind of get the older products if we do miss them. So our initial iteration of the Data Mover Challenge network, as I said, was an extended VLAN network connecting the US, Europe, Saudi Arabia, Australia, and Singapore. The 2023 iteration also expanded our coverage out to South America with the help of Red Clara and RNP in Brazil. So the 2023 network covered 5 continents, and we welcome South America. We were modelling 2 data transfer scenarios. One, 100 gig RNA production networks, and secondly, Starlink for field-based data acquisition. I'd like to thank our Japanese colleagues for supporting us with Starlink capability. We had the opportunity to use this in an impaired weather condition. So there was a typhoon crossing Japan during at least one of the events, which really gave us the opportunity to model how Starlink would operate in a compromised environment. We also have a plan to increase the capacity or increase the extension down to Antarctica. One of our network engineers smuggled 8 Starlink dishes down to our Mawson base, and for the first time ever, people who were overwintering were able to watch Netflix, were able to contact their families at home, video conference. It made a radical difference to the mental health of people overwintering. So we're keen to have every continent on the planet be involved in this. And some pictures from Antarctica. So our network partners, you can see there, are the NRENs, which we're all part of, and I'd like to thank everyone who participated in providing access to their bandwidth, in having their senior network engineers mentor junior network engineers, but most importantly, to give us access and to give commercial organisations access to our R&E networks for a limited amount of time where we could observe what they were doing, and if they were operating in a way that was either performant or non-performant for our existing configurations. Our DTN partners were also around the world. Our friend Joe Manbretti at Starlight was instrumental in providing a large number of DTNs. I won't go through all of the partners, you can read them there. So the challenges to large data transfer over global R&E networks. So disk management, the management of files for efficient transfer, access management, integration with federation services or single sign-on, protocol adaptability, operating system tuning, scheduling processes, I/O strategies, etc., CPU, I/O and network latencies, the lots of small files problem, parallelism, keeping the network full, and performing dynamic adjustments to your tool based on networking conditions. Our judging panel was made up from Professor Francis Lee in SIG, Professor Paulo Grosso from the University of Amsterdam, Hirotaka Sato from APAN-JP and KDDI, Akita-san from JPAN-JP and KDDI, Marcos Felipe Swartz from RNP in Brazil, Tim Chone from JISC in the UK, and myself acting as the Chief Judge. In 2023, we had 6 teams participating: Team Falcon, Team Saito, Team Livewire, Team Ushishino, Team Justice SH, Team RSync, and Robust HPC Alliance. Each of the teams took a fundamentally different approach to the problem. Team Falcon was a PhD project inspired by hands-on experience. And their approach was to have an understanding or heuristic of the data to provide the best insight to methods of data transfer. So compacting lots of small files, using parallelism for large file transfer, and they pre-profiled the data set. I created the data set by combining operational data from both genomics, satellite observations, lots of small files, and basically a wide distribution across the whole range. Team Falcon also introduced a model of heuristic feedback between the sender and receiver agents, which was dynamic. That was applied to I/O optimization and network parameter adjustment. Team Saito had a DTN optimization using dynamic network estimation and DTN impedance matching. This was sponsored by Sienna in their Environment for Network Innovation testbed. They used automation and AI to optimize the transfers. We have a homogeneity of DTN deployments. No two are alike. So we're trying to we're using production services that people are able to loan us. They were evaluating switch buffer size, host buffer sizes, timely delivery, and adapting to non-deterministic network conditions. They provided a DTN as a service layered on Jupyter notebooks, which was a really, really fascinating way to do it. Team Livewire was entered by Architecta, an Australian company that NCI and Pawsey used for data management. Their product Livewire provides a complete fabric for data management and transfer, metadata-driven automated replication, deduplication, and distribution, used parallel streams, provided a visualization of data flows for rapid performance indication, and virtualized the storage layer for optimized I/O handling. Those of you who attended Supercomputing 23 and 24 may have seen the Architecture booth where they were demonstrating network flows in real time. Team Mushishino was from the University of Tokyo in Japan. They had a high-performance and flexible protocol and its application challenges of high-speed transfer at 100 gig over global long-fat networks. They have a protocol called HPFP, designed to perform well in impaired network conditions. This work was based on natural disasters in Japan and making sure that data was available in the case of a natural disaster. They used a UDP-based design rather than using TCP for long-fat networks with packet losses, and provide a socket-based implementation to provide a TCP layer equivalent. They have multiple modes: fair, modest, aggressive, and more. And this performed extremely well over Starlink during a week of torrential rains and storms. Team Just SSH was the standout for me. This was a PhD student from the University of Arizona. He had a replacement to SCP called MSCP, which uses parallelism, requires no host end tuning or differences, uses standard SCP on the host end, but provided an immediate 10-time performance increase over standard SCP. The judging panel basically were compiling this and testing it while we were running the evaluation interviews, and we were all just blown away with how good the product worked. It was able to adjust and tune parameters based on observed performance, but as I said, delivered 10 times performance over standard SCP. Team Racing and the Robust HPC Alliance are a commercial company in Malaysia and China. They use a UDP-based adaptive tuning protocol. From all intents and purposes, it is a direct lift rip-off of, excuse me, it slipped my mind, Aspira, so using many of the same techniques, but at a much lower cost. They excelled in degraded network conditions. Their main work is in shipping, video production and gaming software out of China, using compression, adaptability to firewalls, and provided an effective high throughput from the field. And also provided a complete end-to-end data management platform. So that kind of concludes my presentation on the Data Mover Challenge. We're still pondering when we're going to kick this off again. We think we've kind of exercised most of the capabilities of 100 gig. So we'd be keen to look at running over 400 gig networks or extended Starlink networks. So those of you who are looking at Starlink, we'd be more than happy to contribute our expertise or potentially test some of your systems. So does anyone have any questions? Excellent. Thank you very much, everyone. And I think we've got one more speaker. So our next speaker is Lily Zhang and Jingzhang Li from the Computer Network Information Center, Chinese Academy of Sciences. Over to you.
Thank you, Chair. This is Lily, and please let me share my screen, camera on, and can you hear me?
Yes, we can hear you fine.
Thank you very much. I think the first thing for me probably to say apologize that I had thought we are in the same time zone, so I had a late joining. Let me see. This is my slide, and this is Lily from the CST Cloud and the CST Net, and I'm the manager for international relationship for CST Net. And our report is how we promote the open science by our technical framework. And as you see, so far, open science is very popular in many ways, especially to promote the research in different domains. And based on that, actually, under the umbrella of Chinese Academy of Sciences, we are also facing similar things like data-intensive and big data research. And there are many different research infrastructures under the CAS umbrella. We have the data, we have the research of large scale connected to the world. We have so many partners. So among all of these issues, we probably, for our center, we come from the Computer Network Information Center for CAS, and we are the e-infrastructure service provider to support the CAS level researchers. And as for us, we are the Chinese Internet birthplace. And we have data, and among all of this, we also facilitate service delivery to boost science discovery in different domains. So for our e-infrastructure as one of the national research infrastructure, CST Cloud tries to promote research discovery in different domains. And we do several things. You can see more clearly from this kind of service portfolio, I think. And the internet connectivity is one of the fundamental things. And based on this, we also established integrated framework, and we developed the service softwares and collaborated with third-party service providers, and we provide the end-user kind of different services also. And based on this, we get connected with research infrastructures from CAS and around nations. And you see, the internet connectivity is one of the very important things. It's the ever start of every dialogue and every research. And from CST Connect as an evolving research and education network, we get connected with domestic and international levels. And thanks to the collaboration with all of you, we just get engaged in different global international research initiatives, and we get better connected almost to the world. And based on the infrastructures, there are also some other services, the cloud services based on this internet connectivity. And for one of them, let me see, that's not working. One of them is the cloud service delivery. So based on the fundamental network connection, we are providing compound solutions to get different separated resources better managed all together. So we can just share those resources for better collaborative research. And this page just show one of the work we have been doing so far for the cloud service delivery. And through this service delivery, we see that probably is not enough. We still need to do something more. So in 2021 and even earlier, we proposed the idea why not to enhance the e-infrastructures through technical policy and domain demonstration to highlight the accessibility of resources, interconnectivity of internet, and interoperability between different e-infrastructures, and the inclusiveness of engagement from the world. So from the new initiative, there probably will be a lot of things we do, like from the internet connectivity layer, from the cloud services layer, from the data domain, and large-scale collaboration layers. And you can always find that internet connectivity is one of the most important part. And I think a lot of things we have been discussing is trying to develop a kind of a research network. It could be fully scalable end-to-end, and it could be a software-based tailored network to support research and education research in particular domains. And so through this kind of idea, we also developed a test bed. And through this, based on the internet connectivity, the better performance the network, we are trying to provide one-step virtual community that we have integrated data resources, and we have almost the interested research communities collaborate together, and they could just share data, resources, coding, algorithm, and all of things online, and to support their domain demonstrations better in larger scales in dealing with more complex questions and something like this. So from this, you could see some of the preliminary work we have been so far, and that's not the whole story. And through this, we also have something like the domain demonstration. For example, in astronomy, especially for the FAST program, the CST-NET and the CST Cloud has been engaged to develop an advanced network for large-scale data transfer across different regions. And we also developed a tool called Scalar Box to redesign the work pipe flow. So when the data captured from facilities and between the other end with scientists, there are kind of a redesign of the workflow and some kind of a processing tool to facilitate the managing, the processing, the analysis of the large-scale data and make it more intelligible for knowledge discovery and something like that. And another very interesting topic so far is sustainable development goals, like for disaster mitigation and something like this. And for CST Cloud team, we have been collaborating with our strategic partners on several selected SDG goals. And through our collaboration, we collect the data from different domains and establish a kind of integrated research platform. So through this integrated platform, we have the data resources sharing, we have the tools and algorithms, and most important is we make this service streamless through the workbench. So you can just explore different resources and it could support different SDG goals, research and decision making and something like that. And through different collaborations, we have a dialogue with our internet partners, and we also do several things to promote the technical capacity building in different regions. And so far, especially under the JISC umbrella, we have been doing many, but I think more will be on the road. And through this different discussion, we are developing policies, inclusive open science policies altogether. We are trying to make more communications and conferences on how to develop the more technical policy and domain scenario tailored kind of a guidelines and how we promote this work done. So from these different works, I think there are a few things we can see. The first is the internet connectivity, especially enhanced cyber infrastructure. So really as the fundamental to promote open science in different domains and especially for the sustainable development goals. And for our institute, especially for CST Cloud, we probably will promote the enhanced internet connections with the support of you all. And our research focuses will mainly focus on three different parts, like the internet connection with the world and compound cloud solutions and adoptions of cutting-edge technologies such as the artificial intelligence and something more. And through our APAN conference this time, we have our colleague in the I think there is a particularly an AI adoption for a network session that one of our technical colleague has been sharing some of the work they have been doing using AI tools. And we probably will be quite eager for more open science collaboration with you all. And for this short talk, I just make a brief introduction about what we do from CST-NET and CST Cloud and also our Global Open Science Cloud initiative. And we probably will have some of the upcoming discussions, which we will release more information and welcome for further inclusive and open science dialogue. That's it. Thank you.
Thank you very much. Does anyone in the room have any questions? Okay. Thank you very much for joining us today. Very fascinating presentation. I forgot to thank Simon Peter Green, who was the absolute pivotal person herding the cats across 5 continents and multiple NRENs and multiple providers. Certainly a baptism of fire for Simon, and I can see he's starting to get a few grey hairs like many of the rest of us. This wraps up all of the presentations. Unfortunately, I've been in other sessions and haven't been able to join network engineering. Would anyone like to have any further discussions, or can we all just have a bit of an early mark? I think the early mark seems to be the one. Thank you everyone again for joining us. Thank you for providing the underpinning foundation for all of our national and international research and science. It's down to your hard work that we're all able to support our communities. And I hope to see you again at APAN60 in Hong Kong. Thank you.